All right, so this week we're going to look at some of the derivative stuff that we mentioned last week but couldn't quite get into. And then we're going to go over Newton's method really carefully and think a lot about why we're doing certain things. And then we're going to use Newton's method as a way to solve constrained optimization problems. So these are things that you've seen Zach do in class, but similar to the first recitation, these are, I guess, very fundamental as far as optimal control goes, and really understanding them and being comfortable using them for new problems is going to be critical all semester. So even though it may seem like a little bit of a review and we're going over kind of basic stuff, you'd be amazed at how important really understanding all of this is. So now let's get started with derivatives, which everybody here has seen before, probably different definitions of it and everything. So we're going to try and find one unifying way that we're going to talk about everything, then hopefully get everybody on board. So let's talk about some function f. And f is going to be, and I'll explain this notation in a second. So when you write this right here for a function f, what this means is func name, and then it just means there's n inputs, m outputs. And again, we're assuming here that there's like a vector coming in and a vector coming out. So if I have, y equals f of x, what I'm saying is that y is a vector in Rm, x is a vector in Rn. And sometimes you'll see for functions that have multiple inputs, the signature will be a little different. Specifically, if we have some sort of y equals g of a and b. This is not super important, but if you see this notation, this is what this means. And this is, we'll write this as g, and then just a nice little tuple of whatever a is. So yeah, not super important, but when we write this, this means that there's one input, one output, and here are the sizes of the input and the output. So anyways, let's talk about the derivatives of this function and what we care about. So very specifically, let's talk about partial derivatives. So partial derivatives is just delta over delta. Sorry, the del over del. So del in LaTeX. This is different than the full derivative, which is d over d. So partial looks like this, full derivative looks like this. So for instance, if I had, y dot, this is a derivative with respect to time, this would be d of y, d of t. What we're talking about are partial derivatives. So this is partial of y with respect to partial of something else, maybe x in this case. All right, so now let's get into it. So if we have this function f takes in x, which is a length n, and spits out a length m vector, the first derivative I care about is the Jacobian. And so what the Jacobian is saying is I have partial f, partial x, and this is a matrix. And these dimensions are super important, and sometimes people will get this wrong. So the number of rows is the number of outputs you have. So number of rows equals number of outputs, which in this case is n. And number of columns so the size of the Jacobian is specified by the length of the input and the length of the output. And again, we're only focused on functions that have one vector in, one vector out. And what this looks like is dy1, dx1, dy1, dx2 to dy m. Sorry, no, 1 dx n, right? No, it's m. Yes. hold up, there's X inputs. Sorry, these are wrong. I mixed these up. This should be N, M, because there's M outputs. Hold up. Okay, X is a Rn vector, which is the number of inputs, which is the number of columns. This is N. The number of outputs is Y, which is M. Okay. And then if you imagine we just keep walking this thing down, so we'll do now this is Y2, dx1, Y2, dx2, dy2, xn, and we keep walking this down all the way to dy m dx1, dym dxn. So basically it's just a way for us to organize all of the partial derivatives that we care about for each input and each output individually. And these are all scalars. So this is a matrix of scalars. Okay. Now, the next thing we can talk about is a different function. So this is the Jacobian for vector valued functions. So vector in, vector out. The Jacobian is the best I can do as far as the most meaningful derivative I can come up with. But what if we have a function that has a scalar output? Then we have a few more options. So if I tell you that I have some function g, and I have y equals g, actually I'll write this as if it's a cost function. So I'll do y equals j. Actually, no, I won't use j because j is Jacobian. Okay, we'll go back to g. Y equals g of x. And this time x is in Rn and y is just a scalar. So this will show up, this is like our cost function or our loss function. It's going to take in some vector x. These are the decision variables that we're optimizing over or whatever. And whenever we have a vector coming in and a scalar coming out, there's two different types of derivatives we can come up with. So the first is, again, just like any other function, I can take the Jacobian of this. So if you remember what the Jacobian of this looks like is that this is d del of g, g of x, and we have the number of rows as we have outputs. In this case, we have one output since it's a scalar output. So this means that our Jacobian is a row vector. This is d g dx1, dg dx2, dg dxn. So very importantly, this is a 1 by n row vector. So the definition of the Jacobian does not change. Whenever we have a certain number of outputs, that's the number of rows we have in our Jacobian. But for convenience, we'll go ahead and define something called the gradient that just makes our lives and notation a little easier later on. So the gradient only applies to scalar functions. That means scalar on the output. Then we write it as like this, and all this is just g. And all this is just an Rn vector. So literally all we're doing is we're taking our row, which is our Jacobian, and we're just transposing it to make it a vector. If you imagine, this is super nice because oftentimes in languages, we like talking about vectors and matrices somewhat separate. So storing like a row vector is like a little bit weird. But mathematically, this is like the correct definition of the Jacobian for a single variable output function. But in this case, if we're doing optimization where you like using a computer, using Julia or Python, we treat vectors differently. So since this is just, a one-dimensional piece of information, why not just put it into a vector itself? So this is all the gradient is just the Jacobian transposed in the case of one output functions. And then that leaves us to, and I'll write gradient The next thing we have is the Hessian. And the Hessian is the Jacobian of the gradient, if you can think about that. So all this is you write it as this squared x g. And here what we're doing is we're taking all the possible partial derivatives twice. So if you imagine this is d of g, and we're going to go through and just keep doing this over and over again. So we'll do dg x1, x2, and we just go add all these things each way. Partial of, see, I have a nice image of this. I'll just go ahead and write it out. And this is a n by n symmetric So not always, but for every sort of function that we would care about in the real world, this Hessian will always be symmetric, which is nice because it means that we really only have to evaluate a little more than half of it to collect these values. And with modern like auto diff tools, we actually don't have to do any of that. So it's pretty nice. But the question is, why are we doing things this way? Why are we writing out these gradients in the way that we are? So we have, our Jacobian is written like this. We said this is like the correct mathematically everything. The gradient is what we define as far as just convenience, just to make our lives easier. And then the Hessian is, again, just the Jacobian of the gradient, so the kind of the second derivative of everything. Now, as Zach goes over in class, like the reason this is correct is because if you think about the Taylor series of this, we really should be doing things in a way that the matrix multiplication makes sense. So let's take a look at that real quick, and this will lead us into Newton's method. So if you remember Taylor series, I'm saying that I'm approximating some function f with, some x at some value, x bar, plus the Jacobian.
I have a question.
Mm-hmm.
Why is the gradient the transpose of the Jacobian? Because in the Jacobian, each function is along the rows and each variable is along the columns, right? And in the gradient, since we have just one function, it will be just the first row of the Jacobian, right?
Yes, exactly. So again, the gradient only applies to functions that have one output. So in this case, we're talking about a function f or a function g that spits out a scalar y. And this means that the
Right.
Jacobian is a row vector, like exactly what you just said. We have one
Yes.
output, so we have one row. All we're doing with the gradient is we just transpose that just for convenience, and we make it a normal
Oh,
vector.
oh, okay.
So
Okay,
like
got it.
in Python, Julia, MATLAB, we treat vectors and matrices differently. And so it usually makes sense to think about things. If it truly is just like a vector type of information, it makes more sense to think about it in terms of a vector. If you imagine if we do like gradient descent, which we'll go into in a sec, just having everything be vectors already makes our lives much easier. Does that make sense?
Okay. Yep, okay. Thank you.
Cool. So this is our Taylor series first order for a function, and very important. This is approximately. And if we wanted a full Taylor series, we'd have to include all the other terms. But let's just look at one of these things and let's look at the dimensions of everything. So this is length n, this is length n, and this right here is one row, n columns, and shall do all these. I'll write the full 2D things for everything. So you see how all the dimensions line up here? Or this is not. This is one row. sorry, this is a scalar function I'm doing this for. So let's go back to our first example. That'll make this more clear. So our first example is y equals f of x. The input is Rn. The output is Rm. So this means that this is M1. This is M1. Then our Jacobian is the number of outputs as rows, the number of inputs as columns. Then x is N1. So if we look at these dimensions, so this is a length m vector, and once I multiply this becomes a length m vector. So you see how the definition of the Jacobian in that we have a number of rows, number of columns as our inputs and outputs, respectively. It just makes all the dimensions work out. Now, if I was thinking of like a single variable function, I'd have to transpose things. So if I was using our g example, g of x bar plus gradient of g at x bar, I have to transpose this for it to work. So not super important, but just if someone's ever like asking you like what the Jacobian of a single scalar valued function is, the Jacobian is always going to be a row vector for one row for each of the outputs of the function. And Zach makes a big deal of this, and you'll see this kind of butchered everywhere and done differently, especially with first order optimization stuff. So a lot of like modern machine learning that cares a lot about gradients will just kind of assume that the gradient is the Jacobian for a one-dimensional function. But if you look at the Taylor series, it actually doesn't make sense unless we do things out the right way. All right, so now let's talk about probably the most important idea of the class, which is Newton's method. So I will first start this with just like a general, I guess, like a very high level conversation of, my little brother is like a CS person. And so he and I were talking about this once, and it was like clear to me, it's not super obvious why we're doing any of the approximation whatsoever. And I think it's worth like spending a second talking about. So uh, if I sit there and I'm obsessing over like the Taylor series and I tell you I have like, oh, I have the first derivative, which is the Jacobian, then I have some higher order derivatives. I'm doing all this work to approximate functions. Like the average person who's not super into doing all this stuff would be like, why are we approximating this function if we can like evaluate it in closed form? Because oftentimes we have to approximate things or approximating them because we can't evaluate them in closed form. But in optimization, we know these functions, right? I know what my function f is. So why am I forming like all these approximations? So let's think about like a very simple example of I have some function looks like this. If I have some function that looks like this, and I can compute it analytically, so I can just say, y equals f of x. What is the utility of like forming these derivatives and trying to approximate this when I can just evaluate it in closed form? So one example is, say I want to minimize this function. I want to find out where it is right here. The only way for me to do this without forming any sort of approximation is I can just sit there and calculate what the value is at all these different points, which is very, very expensive because I don't know where to actually start. I don't know how tight to discretize. I can use like a bisection search. So I can like, look here, and then cut in half, look here, and keep doing that. So I can do all these crazy derivative-free methods to approximate the solution of this thing. But ultimately, even though I have this function in closed form, that doesn't mean I can just sit there and evaluate it billions of times until I get the answer I want to. And oftentimes we can approximate things as linear or a second order, and we can use other tools to solve these things much faster. So it's not that we can't evaluate the function f, it's that we just don't want to do it over and over and over again. And approximating this thing with the Taylor series sometimes lets us use more powerful tools that get us a solution faster. So if you didn't quite track that, it'll become more clear as we do this over and over in the class, because you'll see we have these functions that we know and we know how to evaluate them. We can write them in code, and we're always going to be doing some form of an approximation of them. And the answer is always because we're approximating because the linear form is easy for us to deal with, and the native nonlinear form is often very tricky. So now let's talk about Newton's method. So why do we need Newton's method at all? And I think first, let's talk about what we can and can't solve, I guess, with the sort of math that you already know. So if I were to tell you that you need to solve, you know, 5 times x, or I'll do a and b, 5 plus 6b equals 7, and then 6a minus 4b equals 19. If I told you to solve for a and b, you could do so. Like I'm giving you, like if there was a solution, you could find it. So if a solution exists, I can find it. So if I give you a linear equation and there is a solution, I can use whatever tool I want to. I can, if we're doing stuff like we did in high school, just go ahead and combine these equations. I can do substitution. If you're doing more linear algebra stuff, I can just put this into a linear system and solve the linear system. So linear things, if there's a solution, we can solve it. And what you'll see in this class is that the linear stuff is kind of the only thing that we can solve. So we're always trying to put stuff into this linear form because those are the tools that we actually can use reliably. And now let's look at a different example, which is say I have, e to the a plus this equals sine of a, and then, a squared plus sine b a to the e equals -1. If I give you some random nonlinear equation, you can't guarantee that you can solve it, right? If a solution exists, there's no promise that you can go out there and just turn the crank until you find it. So not easy. So linear things we can solve. Nonlinear things, really hard to solve. So what is the, like in what I've been talking about as far as why we approximate these things, why that's so important? Linear things are the only thing we can solve. The logical first step is if I can't solve this thing, like analytically, just like kind of writing it down and playing with it, I want some like algorithm that I can use to turn the crank to just kind of solve this thing for me. It turns out that like the answer is approximating, solving the approximation, and then redoing that over and over again until we solve. So what does this actually look like? Let's take a look at a one-dimensional case. Shall do straight lines for your sanity. Okay. So say I have like something like this, and I want to solve where this thing equals 0. So I want to solve a root finding problem. So if you remember a root of a function, this is where I can put in a value x and get out 0. So I want to find the root of this. And you can form all nonlinear equation solving as root finding problems. That's really important. So if I'm trying to solve f of x equals y, I really just want to solve f of x minus y equals 0, and find roots of this. So I just kind of moved from solving equations to root finding. Same thing. I can take any equation I want to, I can turn it into a root finding problem and use Newton's method to find the roots. So let's talk about finding roots for a very simple function. This is y equals f of x. We got x, y. So going about the kind of the way that we've been thinking about these things, say my current iterate. So this is going to be an iterative solution. So I'm not going to solve this in closed form. I'm going to use an algorithm that's going to iterate a bunch of different best guesses of x until I converge to close enough. So my current best guess, I'm going to initialize. And again, all Newton's method, root finding, nonlinear equations, we always need an initial guess. And the initial guess is very, very important. So in this case, our initial guess is, okay, maybe this is close to the root. So what I do here, I form a first order Taylor series. So what does that mean? That means I linearize the function and I approximate it as linear. So if I approximate this function as linear, what does it look like? It looks like this. So I approximate this function as linear. And then once I've done that, I say, okay, this is where, according to the linear approximation, because again, linear stuff I can solve, the linear approximation tells me that there should be a root right here. So then my new value of x becomes this. And then I take this function, I do the same thing, I linearize it. And that gives me my next value, x of 2. I take this, I linearize it. And now I'm really close. So just in a few different steps of linearize, solve over and over and over again, I converge very quickly. So let's look at what this looks like in terms of the actual math. So what I'm saying is that I have some function y. So I have f of x equals 0. Root finding. So f of x equals 0, I'm looking for x that makes the output 0. So what I'll do is I'll take my current iterate x0, and I will form a first order Taylor series of this. I will say that x is approximately my current value plus the derivative of this at the current value times x minus x0. And remember, what I'm saying is that I want to solve for when this linear approximation equals 0. So sorry, this is not x, this is y. So I want to solve for when y equals 0. So what I do is I do 0 equals current value of this plus our derivative. I'll just copy it. And this is solve for so solve for the root of our linearized version. So now we just substitute things. Now we say, okay, f of x f of x0 equals negative. I'm going to call this j. And then what we see is I can just do, let me find a better way to write this. Would be a little clearer. Okay, I guess it's okay. Actually, I don't like using j yet. I feel like it's too. Put this all on one page, so it makes more sense. So if I have this right here, I want to solve for when this equals 0. What I can do is I can do f x of 0 equals negative df dx x0 x minus x0. Okay. Now if I invert this thing, apply it to both sides, I get negative df dx x0 inverse f x0 equals x minus x0. So what this tells me is that my new value of x that solves this root finding problem is x0 minus df dx at x0 negative 1 f x0. And now if we think about this in terms of like the iterative solution of this, and I assign like index values to everything, I can say x of k plus 1 equals x of k minus df dx x of k. And this is Newton's method. And all we did was we formed a first order Taylor series of the function, and then we did the root finding problem because again, linear stuff we can solve. So we solved the root finding problem for the linearized version of this, and this just gives us this nice recursion right here. So I can just iterate on this until I solve it. And now let's think about another maybe more intuitive way to think about the variable naming that we're going to do. So now let's talk about these deltas. So if I want to like do, say I want x to equal xk plus delta x. And in this class, we'll go through a bunch of different stuff where we use deltas, and deltas show up in control. It's all it is we're just finding a new variable that we're throwing in here, and then we're just defining it to be something. So if I just define x to be xk plus delta x, again, this doesn't come from anything. It's just I'm just saying it is, and so it's true. This is, by decree, if you will, I'm saying that this is what our delta x means. Now, if I go and I substitute this into our original equation, what we see is we get f xk plus df dx xk, and then x minus x0. This is what we're going to look at. This is xk. Okay. This is xk plus delta x minus xk equals delta x, because these things cancel. So all this tells me is that I can just write this out as xk plus df dx xk delta x equals 0. And then delta x negative df dx. So these are the two versions of Newton's method you'll see. They're the exact same. They just, one of these uses a delta and one of them just gives us the recursion. Now the question is like, why might this be important? Like why might we care about like the way that we write this thing down? Like if they both convey the same information, why does it really matter? And the reason it matters is because when we're doing optimization or we're doing root finding or anything, we often want to think about things in terms of steps. So I have a current value of xk. I want to figure out what the step is to my xk plus 1. And this delta is nice for doing that. And the reason why is because sometimes our linearization is not that good. So I don't really want to take a step in the full direction. I want to take a shorter step. So I want to use like a line search or a step length or a learning rate in machine learning. I want to use some different thing to scale this by. So oftentimes what you'll see for an actual implementation of Newton's method, like you guys will do in homework 1, is what we're really doing is we're doing x of k plus 1 equals xk plus alpha, and then do the Newton step here. So and we call this the Newton step. So just to recap what we just did right here, we started out by saying if some function f of x equals y, I want to solve for when y equals 0. I want to solve the root finding problem of this. So I linearized this thing. I formed a first order Taylor series. And then I solved for when that linearization equals 0. And then I says, okay, well, let's think about things in terms of deltas now. So I will just define, delta equals x of k plus delta equals our new x. And then I will substitute that in, and what we'll see is it just lets us write down, the Newton step itself, which again, this and this are the exact same, just the step between iterates. And once I define this as a Newton step, I can then be a little more generic in how I write down Newton's method. And I can say that I will just apply a Newton step, but I don't have to apply the full step if I don't want to. I can just have some learning rate alpha that will tell me what I should be doing, like how much I should be stepping. So what we've just done is that I can now give you any f of x, any initial condition, and you can just turn the crank and use Newton's method until you solve it. So if I do input these things, use Newton, And then we're going to solve this when, we have some convergence criteria. So how does Newton converge? So Newton converges like insanely fast. So if you looked at this example, this is a dumb, just like graphical example. But what we should have seen is that, our first answer is off by a lot. Our second answer is off by a little. And the third answer is like basically perfect. So this thing seemed to converge pretty quickly. So when we talk about convergence rates, you'll see, a linear convergence rate, super linear, quadratic. Of the convergence rate, Newton basically has the best. So what this means is that if I have a plot and this plot shows me, you know, the norm of f of x, remember I'm trying to zero out this, so the norm should be 0. And this is iteration. What we'll see in Newton's method is that if we're in the basin of attraction, so we're in where we are if we start converging, this thing will plummet like this. Like we converge extremely quickly. And this is because we have quadratic convergence. Quadratic convergence. And this just means that the error at the next time step is about equal to this error squared. So if you imagine if I have 1e minus 4 is my current error, 1e minus 4 squared is 1e minus 8. So now I have like a pretty dramatic decrease in my error. So this is why we really start to plummet down here. So basically, your takeaway from this, Newton's method is extremely fast to converge in terms of number of iterations. And once we're in the basin of attraction, it will converge quadratically. So very, very quickly. And the full story is if I give you a function and I give you how I want to initialize, so my initial guess, then I can just use Newton's method where I use whatever I want to for the line search. Sometimes I don't have to use one. Sometimes I have to use one. And then I just solve this thing once the norm of this residual is less than some tolerance. And I can decide what that is. Maybe I want an exact solution, and I should wait until this thing goes down to machine precision, so 1e minus 15 in a computer. Sometimes I want that. Sometimes I just need like an approximate solution. So like 1e minus 3 is okay. So how you choose this tolerance is very problem dependent. And generally in control problems, we can be pretty lax about this because if you ever work with a robot, the way that we actually control these things and the actuator commands that we send to the motors, there's like a little bit of error in those things anyways. So we don't really need to get down to like 1e minus 15 if we're just sending, relatively coarse commands anyways. So this tolerance, context dependent, and controls, we're generally pretty lax about this. So now that we have this tool, let's do some optimization. We explain why we look at the norm of. Did I say less than 1 somewhere? So sorry. So the question in the chat is, could you explain why we look at the norm of f of xk less than 1? Shouldn't we be looking for f of xk close to 0? So yes. Do I have something where I say less than 1? Oh, sorry. This is tall. Tall is intolerance. So tall is tolerance. So it's like, 1e minus 3, 1e minus 6. Or if I want full machine precision, 1e minus 15. Yeah. Super good question. And again, this is not like different problems will have different convergence criteria. So here I'm just saying like norm of f less than some tolerance, but maybe it's like the L1 norm, maybe it's like the infinity norm. There's a bunch of different metrics that are all problem dependent, but we're going to use some criteria to determine like when we're close enough to a solution that we can stop using Newton's method. Okay, so now let's take a look at optimization and why, like everything I just said for Newton's method was root finding. Like I didn't say optimization once, I'm just focused on root finding. So how do we take what we know from root finding and use this to solve optimization problems, which is how we're going to use it in this class over and over again. So for this, let's first look at unconstrained optimization. So by that, I mean I'm optimizing a objective function with no constraints. So I want to do min. I want to minimize this right here. So if I write down what the optimality condition of this is, I get the gradient of f must be equal to 0. So once the gradient of f is equal to 0, I have a solution. If this is a convex problem, I have the global solution. If it's a non-convex problem, I have a local solution. But what I'm doing is I'm finding a minima of this function f. And the way we do this is, I wrote down this condition. This is our optimality condition because there's no constraints. It's super simple. I just say make this thing equal to 0. And the way that I start doing that is just using Newton's method. So now I just say that if I just define g as this gradient function of f, and I want this thing to be equal to 0, now I just use Newton's method. Now I just say xk plus 1 equals xk plus g x xk. And then what I said earlier about the derivatives is that the Jacobian of the gradient is actually the Hessian. So this is Newton's method. So this is Newton's method for unconstrained optimization, is if I take my problem, I look at the optimality condition. This is take a look at the optimality condition, and then I say that, okay, I want to set this thing equal to 0 using a root finding method. So I've turned my optimization problem into a root finding problem using this. And then I just plug it into Newton's method. And then I recognize the fact that the Jacobian of my gradient is my Hessian. And what I get is I get this right here, which is just saying that, this Newton step I'm calculating is going to be the Hessian inverted times the gradient. Okay. So this like general idea like should be somewhat familiar if you've seen this. And what you'll see is that people will often conflate Newton with a quadratic approximation of the function versus a linear approximation. So everything that I've said so far about root finding, I took my function, I linearized it, and then once I linearized it, I solved the linear version of it. So Newton's method is forming, when root finding, is forming a linear approximation of my function and solving that linear version of it. Now, the reason that you hear people say like, oh yeah, well, Newton will perform, like a second order expansion of the function and solve that. That's only true when we're doing optimization. And the reason why is because our optimality condition already has one derivative in there. Wouldn't the Jacobian of the gradient be the Hessian of the original function? Oh, sorry. Yeah, good catch. This is f. Thank you. Um, yes. So another lens we can look at this as is if I have my approximation of it. So say I take my function f and I form a second order Taylor series. And I'll do this in terms of delta x. So I'll do f of xk plus gradient of f k transpose delta x plus 1/2 delta x transpose. So if I approximate my function like this right here, what I get is I get a new problem that says minimize with respect to delta x this thing right here. And now let's write out the optimality conditions of this. So if I take this problem and I just say, okay, given this thing right here where I'm optimizing over delta x's, delta x, delta x, delta x. This is a quadratic form, so it's very easy for me to take any derivatives I want to. And all I'm saying is that in order for this to be optimal, I have the gradient of this function equals 0. The gradient of which is just this And then when I go and solve this, I get and again, I see Newton's method the same way I wrote it up right here. This and this. The only difference is that here I put our step parameter alpha, but we can do the same thing right here because this is just delta x. So I'm really just computing this right here. So you can see how when we are doing root finding, we take this function, we linearize it, and then Newton's method will solve the linear version of that root finding problem. But when I'm doing optimization, the root finding problem itself is on the gradient already. So what I'm saying is that I have some function f, I want to root find, so the gradient of f equals 0. And that's why if I do Newton's method on that, then I see a second derivative, I see the Hessian. And this is why people will say that Newton's method for optimization is really forming a second order approximation of the function and solving that, when really it's just forming a first order approximation of the gradient. So I will try and write that a little more clear. So I have, you know, so root finding is just going to take an arbitrary root finding problem and linearize it. So it's going to be linearize plus solve. And then we just repeat. So root finding is linearize, solve over and over again. Newton's method is the same thing, linearize, solve, but now I'm doing it on the gradient of the function. So the linearized version of the gradient function is going to involve the Hessian, is why this happens. So you'll play with this in the homework. It'll make like a little more sense as you start working with it. But always understand that Newton's method is just a root finding method, and it's being hijacked to use for optimization. And the same is true of constrained optimization. So this is something that you'll do in your homework. Zach's gone over this in class. I just have 10 minutes, so I won't spend a ton of time on this, but relatively straightforward. What we're looking at is if I have a constrained problem, let's start by writing out the optimality conditions. So this tells me that I have a Lagrangian that equals f of x plus lambda transpose c of x. And then my optimality conditions, the first one is called stationarity. This is the gradient of the Lagrangian equals 0. So in this case, it's gradient of f plus so this is our first condition. Our second condition is that c of x equals 0. So here are our, so this is optimality. Here are KKT conditions, which is just our optimality conditions for this problem. So if I'm looking for this, once again, I took a constrained problem, I wrote down the optimality conditions, and once again, I have a root finding problem. So I will use Newton's method, and I will use our root finding method to find the solution of this. And the way that I do this is actually pretty clever. So I think about things in terms of, say I have some new variable z, just a concatenation of them both. What I say is that I have some function, I won't use f, I'll use r of z equals, so you see now that if I'm solving over this variable z, that finding a solution to this that satisfies the optimality conditions, so finding the solution of the problem, really just involves me solving a root finding problem for this specific function right here. So if I go and I start taking my Newton steps on this, the first thing I do is I will form the Jacobian of this right here. So I'll just go ahead and copy this over to this page. So I will form the Jacobian of this. Remember my Newton step, delta z is negative r c CK. This is, the definition of the Newton step. So now let's apply this to our specific problem. So what we see is that we have delta x, delta lambda equals negative. And now let's form the Jacobian of this. And this is where we get the Hessian of our Lagrangian. Our constraint Jacobian. Transpose. So this is how I compute Newton steps for this system. And there's one term here that we haven't quite talked about. So this, we wrote out what this is. Here's our constraint function. Constraint Jacobians, pretty straightforward. This is the one kind of term that we're still a little unsure about. So let's spend a second think about what this would be. So earlier I wrote that this is our Lagrangian. So what does the Hessian of our Lagrangian look like? So our Hessian is, first let's form the gradient. Here's the gradient. Now what's the Hessian? This is Hessian of the cost function. And then we have this d dx of dc dx transpose lambda. So this term, this is very easy for us to compute if we have a simple cost function. Computing the Hessian of the cost should be okay. This term is kind of difficult. So this term involves me taking a constraint function, I differentiate it once, and then I differentiate the whole thing twice. And if you think about this, this is like I'm differentiating a matrix now. So now I have like a lot of terms. I have a third order tensor, and this is totally doable. Like modern computers, modern autodiff frameworks have no issue doing this. It's oftentimes just very expensive to compute the second derivative of the constraint function. So this leads us to a kind of a generalized version of Newton's method, where I will take this, I will copy, paste. Now opposed to just having the true answer, I will write just a placeholder H. And then we're going to write down two forms of this. So for full Newton, we just have, this is just the gradient, or sorry, the Hessian of the Lagrangian. So for full Newton, this is what I wrote down earlier. This is, the true Jacobian of our residual function is this. Now, if I want to think about Gauss Newton, which Zach has mentioned, where I want to be a little lazier, and I basically want to ignore this term right here. This is called Gauss Newton. Here, my H is just going to be my cost function. So this is the main for constrained optimization. This is our takeaway. If I want to compute full Newton steps, I have to form this term, which can be kind of ugly and expensive. If I just want to use Gauss Newton steps, I'll do this. And so now let's talk about, I guess, why we do one versus the other. So in general, full Newton will converge faster, but there is a little bit of like something kind of sneaky here. So if I choose my cost function like I do for a lot of control problems, normally my cost function is nice and convex. And that means that my Hessian of this thing is going to be nice, and it's going to be a positive semi-definite matrix. So this is nice for us to work with. It'll give us a descent direction. life is easier when our cost function is convex. This right here is called the constraint curvature term. Yes. Then everything about this recitation gets posted on not Canvas, but on the course website, which will then link to GitHub. So to Ben Gu, who asked that question. Um, But if I'm doing Gauss-Newton steps, this is super nice. I get to deal with this. But for full Newton, I have this constraint curvature. And what this can do is it can take my convex cost function and it can basically turn this second derivative, this Hessian, so it has a little bit of a negative eigenvalue in there. So as the constraint curvature can make the optimization problem a little uglier, even though it will converge faster if it's correct, it's generally more difficult to deal with. So in this class, and almost always, we're going to ignore this term and just use Gauss-Newton as often as possible. So takeaway here, I can solve constrained optimization problems as root finding problems using Newton's method. Here is what we're looking for in Newton's method. This is how we compute the Newton steps. This is the Newton step right here. And we have two choices for what we do for H. We can either do full Newton, where we get the Hessian plus the cost curvature, which is the true Hessian of the Lagrangian. Or if I want to be, I don't know, lazy or smart, however you want to call it, we use Gauss-Newton, which is where we just form this with the Hessian of the cost function. So we'll talk about this more. Zach will go through this over and over again in class. And throughout the whole semester, we'll be doing Gauss-Newton, full Newton stuff. So, this will all become very clear soon, why we do one versus the other and why it's actually nicer to do one versus the other. And again, it's different for different domains, but specifically in the controls world where we often choose our own cost functions, we choose this F such that this is very nice. So we really want to use that whenever possible. If it was a super crazy field where our objective functions are very non-convex and difficult to work with, maybe this wouldn't make that big of a difference. I don't know. It's very context dependent, but in controls, since we choose our costs are easy, our constraints are hard. We really want to just focus on the costs in the Gaussian, which makes our life much easier. All right.
Why is the Hessian of the constraint function like a third order tensor? Like, what are the dimensions of the constraint and the cost function?
What are the dimensions of everything? So what you asked is totally true. So if I look at the constraint curvature term, so constraint curvature, this is d of x, dc dx, xk. Okay. So I can do this in two different ways. And I can think about it in terms of like what the dimensions of it are. So I will use m as the number of constraints. So remember the dual variable and the constraints are the same dimension. So if I have m constraints, what I'm dealing with here is that this term right here is the number of, I'll do this, x. So this portion right here, this section, this is an n by 1 matrix. And then this d dx makes this whole thing n by n. And now with modern auto-diffing tools, I can do this. I can just give it this function right here and just say, take the Jacobian of it, and it will do that without forming the third order tensor. But if I want to do it explicitly, I can do it in the following way. I can say, since lambda does not have a dependence on x, I can instead just write this as the following. I can say d of dx of d of c dx. And this is where things get like a little gross. So we have this vector right here. This is m by 1. And then what is the contraction? There's some. I forget how the contraction works for third order tensors, but this ends up being, and this is 1D array. And this is where we get into trouble. We do not want to form third order or three-dimensional arrays ever. This will often just be super expensive. Modern linear algebra things don't really deal with this. So like obviously if you have, PyTorch or JAX or something and you are like doing a batch operation over another one of the rows, that all that stuff is fine. But for normal like linear algebra, doing things with third order tensors is really expensive. So everything should be matrices and vectors, not third order tensors. Dealing with this term, dealing with full Newton involves computing this term. And if I want to use a modern autodiff framework and just compute this right here, then I can do that. It's still expensive and it still adds some of the negative constraint curvature that will hurt the positive definiteness of this H, but it's not like the end of the world. But doing it this way, it really is the end of the world. This is like super expensive to evaluate, and does not work super well on modern computing systems. Does that
Okay,
answer your
and what's the
question?
yes, I think so, yes. And what's the intuition behind the Lagrange multiplier?
In general, or in this problem, or what?
I mean this, I guess.
So, it's the easiest way to answer this. So I'm gonna stop the recording and we'll just turn this into office hours.